So yesterday we talked about 4 alchemists. Alchemists were a special type of scientists back in the medieval times that were super interested in how things were made and different materials and what might happen if you combined them, took them apart, why things were the way they were. And you guys all debated and talked to each other and moved around the room to decide which scientist knew it all.
It was right.
Oh, we're going to be talking about this for a couple of weeks.
Where is?
You're just like, who's right? Who's right? Was I right? Was I right? She's ready. And I'm not going to tell you.
Everyone was right.
Okay? Grayson says we're all right. I know. But Kane and Zeke and a few others brought up something where they said, matter can't be destroyed because one of the scientists said that the particles just disappear, that part of the gargoyle just disappears. It can't just disappear, they said, because matter can't disappear.
And then Sean
can't
said,
be destroyed.
What about babies? Aren't they being born?
Okay. So today we're going to talk about matter. What is matter? And how true is that matter can't be created or destroyed? Close your Chromebooks if you're on your Chromebook, guys. We're ready for science, okay? All right. So I'm looking for volunteers to read today. Today's going to be a reading volunteer day. Maggie, come on up. I've got a paper up here, and Maggie's going to start us off with what matters about matter.
Where do you find things made of matter? If you can taste, smell, or touch something, it's matter. Anything that takes up space is matter. It can come in different forms and can behave in different ways. Even a breeze is matter because air takes up space, but some things that exist, such as heat and light, are not matter. Why not? They don't take up any space. Want me to read the next one?
Yeah, go ahead.
What makes matter up, or what makes up matter? Matter takes up space, but what is it made of? You can break down any object into smaller parts. At first, you can see the broken pieces. Eventually, you would need to use a tool such as a microscope to see the smaller parts. At that stage, the parts can still get smaller all the way down to their basic particles. The smallest parts of matter that exist, you cannot see. You cannot see particles, but they make up all matter. The sun, whales, the air, apple juice, and the ink and paper of this page are all forms of made of particles.
Perfect. Stop there, Mags. Thank you. All right, Lillard.
Are you recording?
Am I recording? Yes, I am. Oh, sorry, I don't have them on. Oh, guys, I'm sorry if the virtual friends are talking. I don't even have the TV on. I couldn't hear you. Okay. So matter is everything. This paper, this popsicle stick, whales, like it said, the wind that's blowing towards the camera, pickles, Parker. But so talk about when it breaks all the way down. So look at this picture on the page, and I get that it's a black and white picture, so it's a little bit harder to see. But underneath the picture, what this is a picture of is like a charcoal briquette, like you would put in like a grill or whatever outside if you were grilling outside. Some of you have a gas grill, but some of you, I'm sure you've seen a charcoal grill. I have a charcoal grill.
I don't have a grill.
Okay, thanks for sharing. If a briquette is broken, you can see large and small parts that make up the whole thing. Now, even the smallest particles are all kind of the same. They all look like this black chalky stuff when you break apart a piece of charcoal. This is because they are made from the same type of matter called carbon. So you see some of those pieces are smaller than others, and some of them just almost look like dust in the picture, right? But I could even break that dust up. If I were to keep hitting that dust and smashing that dust, it would turn into even finer and finer dust. And if I looked at it under a microscope,
It would be part of,
it would be, I would be able to see, if I had a strong enough microscope, I would be able to see the particles in it, which are these teensy things that you can only see with a microscope, smaller than bugs and bacteria. Particles even make up the little bacteria. So even think about this. Bacteria and germs and virus that we've been talking a lot about, coronavirus, you've got to actually look under a microscope to see it, right? And then you see that little thing that looks like it's got a bunch of little suction cups coming out of it, and that's the coronavirus, right? We've all seen the little pictures of coronavirus.
Sounds COVID.
Okay, and then we break it down from there, and coronavirus is made up of different particles, okay? Every single thing, if we looked at it small enough, are tiny pieces of some sort of particle, and those particles are all the elements. So I'm going to look up something real quick for you guys.
Aren't there different types of elements?
There are. That's exactly where I am going with this.
Carbon.
Okay, so this, let me share my screen.
Wow. I know one.
Okay, so this is called the periodic table. This guy here. I know Lily has it hanging on her wall because she's shown us before. I want the picture. Show me the picture. Here we go. This is the periodic table of elements. Every single bit of matter is made of one or more of these things, and it looks like a fancy little code. Okay, but but each of them stands for something. And you're going to learn a lot more about this when you get over to Danby and high school. But I wanted to at least introduce it because those particles, when I break the charcoal down, and I break it down and I break it down, and it's dust. And then I keep breaking it down and I look at it under a microscope. Eventually, I'm going to see particles of carbon, which is number 6. C stands for carbon. Okay, hydrogen, helium, lithium, barium, boron, carbon, nitrogen, oxygen, barium, nickel. I don't remember all of them. Oh, magnesium, aluminum, silver. I don't know all of them. I used to know all of them because I think when I was in 7th grade, we were made to memorize all of them. Maybe it was high school. But I do know that 6 is carbon. It's one of the basic elements. Remember back when we talked about our body systems back before Christmas?
They were talking about poop.
We did talk about poop one day. But more than that, your poop, guess what your poop is made of?
Bacteria.
Okay, carbon. Lily knew where I was going. Carbon. Our bodies are made up of
Carbon.
carbon. We talked about that a lot during the biosphere part we talked about entering our body systems. The air we breathe has carbon dioxide that we give out, and we breathe in oxygen. Our bodies are full of carbon,
Water.
oxygen, nitrogen,
And water.
and water.
Water is number 74.
Water is not number 74. Water is not an element. I don't know what W stands for off the top of my head. Water is a combination of hydrogen and oxygen. It's H2O. 2 hydrogens and 1 oxygen love each other a lot, and then they make a water molecule. Now, this is some advanced stuff. Like I said, this is Danby and whatever, but I just wanted to show you that every single thing that is matter, which is anything that takes up space, if we break it down far enough, it's going to be one of these things under a microscope. A particle of that.
Can you break that down for even more?
Can I break this down anymore? No, this is the smallest you can break it down. Is these things.
Where's phosphorus?
Phosphorus is it K? I think phosphorus is the K.
I think so, yeah.
Well, it won't let me click on it. I'm pretty sure.
We shouldn't trust
Periodic table,
Wikipedia.
phosphorus, symbol. Please tell me I'm right. Do I win? Oh no, phosphorus is the P. It's number 15. Okay. What is the K? I don't know. I'd have to look it up. Anyway, so each Even the tiniest speck of a charcoal briquette is hundreds of millions of carbon particles. So one little piece of dust that we could see is hundreds of millions of pieces of carbon stuck together. Okay? Now, whether that piece of dust is a tiny piece of dust or whether it's the big charcoal briquette that actually goes in your grill, it still has the same properties. It looks black. It feels kind of chalky and dusty. You can write with it, right?
Yeah, it's black chalk.
It's basically kind of like a black chalk is what it feels like, right? And it's something, I mean, its weight is not so, like you can hold it. Even if you had a big piece of charcoal, you could easily all hold it. So it's not very, very heavy. So regardless of whether I have 1 molecule of water or 1,000 molecules of water, water still has the same properties, right? It's wet, it's clear unless we added something to it. Okay, so particles everywhere. Who wants to read next? DJ.
I had a question that
Okay.
you called on me and then Grayson talked.
Oh, I'm sorry. Okay.
Well, it's not really a question. I know that we have iron in our blood.
Yes, we do. Okay, so when I said those few elements that I listed, those were the main ones. But yes, iron is in our blood. There are lots of elements in our body other than the ones I listed. But carbon, water, oxygen, and nitrogen are the biggie ones. Okay. All right, somebody that actually wants to read. Fiona. Particles everywhere.
Remember that matter is made of tiny particles? These particles can rearrange themselves into many different shapes and sizes, but not all matter has a definite shape. Water, milk, and the air you breathe also forms of matter. It is how these particles join together and determine what kind of matter you have.
So if you do it like a different way, like,
It might have a different property.
so,
Yeah.
like if it has like H2O, like that, if you put an O to H, would it be different?
Mm-hmm.
Huh.
Mm-hmm. Yeah. So depending on the number of different things that are stuck together. So like H2O is 2 hydrogens and 1 oxygen. If I had 2 oxygens and 1 hydrogen, it would be something different. It might be something, so I'm honestly not sure. Like you can have oxidized water, which has extra oxygen in it, like H2O2. And I think that's the kind of water that you can actually breathe in because it's got extra oxygen in it.
Silted water.
If you put enough, scientists have a way where they can put enough oxygen in water that we can breathe it. That scares me. I don't want to try and drown accidentally.
I would try.
But yeah, you can have oxygenated water. It does exist.
So if it's like H2O5, that'd probably be able to breathe.
I don't know who was the goofball that decided to test that and be like, I might drown or I might discover something awesome. I'm not.
Well,
I'm
he's
not
not really thinking
But-
he's the big famous.
okay. Okay, so the first little bubble there in the caption. Aluminum is a lightweight metal. It is often used to build things that need to move quickly, including cars. This water bottle is made of aluminum, and it's pointing to this water bottle that this dude is drinking. Some of you have aluminum water bottles. Maybe this one. Probably this one.
I did
Yours
the
is
other day.
plastic because Grace Mom made it. It's a type of, yeah. The
Well,
ones that
plastic.
Grace Mom's made are not
Yeah,
aluminum.
I like
Mine,
My mom didn't make all of them.
I have some.
my coffee cup, probably aluminum of some sort.
Is this aluminum?
No, that was plastic. It's got to this machine to it. But the most common type of aluminum that I think of that we have in our house is aluminum foil. O class,
Oh, yeah.
focus. Aluminum foil. How many of you have aluminum foil in your kitchen?
Yeah.
And maybe your mom's put it on top of food to keep it
Yes.
safe, or put it over the edges of a pie to keep the edges from burning.
Or she puts it in, around the food and then puts it in the grill.
Yeah, like if you're saving some leftovers or whatever, you put a foil on the top
My
sometimes.
mom, instead of having to clean off, my mom instead of having to clean off all of like the trays that you use to put food in the oven. She just puts a sheet of aluminum on the tray.
Yeah. Yeah, you can do that too, so that instead of putting like baking spray on a baking tray, you can line it with aluminum instead, and then the food, the like sticky stuff drains on the aluminum. Okay. But think about it. That's actually metal. But how easy is it for you to like? I mean, you can crunch it in a ball like easily. The wind could even bend aluminum because it's very thin. Now, aluminum is a lightweight metal. If I had to guess, the legs of the chairs are made of aluminum. Because if they were made of a different, stronger metal, we would not be able to lift them as easily, and they wouldn't slide and move as easily. Also, if I were to take a hammer, not my little wimpy hammer that I have here in the classroom, but like an actual like normal grown-up hammer, and I hit one of these chair legs as hard as I could, and I nailed it, right? Like my aim is good and solid, and I had a good solid, I would most likely dent or bend the leg of the chair. Because aluminum, one of aluminum's properties, I don't have the periodic table up there anymore. I think aluminum is actually Al. It's not displayed. It's here. It's just not displayed. Oh, it went away.
No, that's because we looked up on the same tab.
Where'd it go? Oh, I didn't want that one. Whatever. Just come here. Aluminum, I really think it's Al. Yeah, it's 13.
Ooh, now we can actually see it. We can actually read it this time.
Where'd it go?
AL 13.
Okay, 13, aluminum, Al. So whether aluminum is a piece of aluminum foil in your kitchen or whether it is the legs of the chair, it's one of its properties is that it is lightweight and bendable.
What is gold?
AU.
Why is A?
What number?
Because all those the most.
Because I'm pretty sure gold's just another word for it.
Where is it?
It's 79.
Yeah, I'm pretty sure gold is AU.
No, it is.
And what? How
I
do
know
they
for sure.
determine
Okay.
what numbers?
What determined the numbers?
Yeah.
The order they were discovered.
Yeah, that's what I was saying. Yeah, phosphorus was discovered by Mary Curie.
Okay, Madame Marie Curie discovered a lot of them. A lot of the radioactive elements in it cost her life because she didn't know what radioactivity was until it was too late. Cam could tell us a load about it because that was her person that she studied. Okay, the other little bubble down there, it says carbon is a very useful material. We already talked about carbon with the charcoal briquette. We said our bodies are made of a lot of carbon. We know carbon dioxide is something that we breathe out.
Cycle.
Okay. Carbon is a very useful material. It can be found in charcoal in your grill. The sweet tea you drank earlier.
How does it know we drank sweet tea?
I don't know, but I wish I had sweet tea.
Yeah, now
And in the soles of your shoes, even you might have carbon. Carbon is one of the most Carbon is one of the most common elements that you can find. You see it's number 6. It was discovered, like Zeke said, these are listed in the order they were discovered. It was discovered number 6, one of the very first elements because it is so plentiful. It is easy to find. Lots and lots of things are made of carbon. It's all over inside every living thing.
OG is the hardest one to find.
No. There are, is there more than that now? I don't know. I don't know. Some of these didn't exist when I studied this chart. I feel like the chart only went to about here-ish when I was your age. Things are still being discovered today.
Wow.
Hey, Miss Fab.
All right. Now listen.
This is gonna be hard.
Where's is there fluoride on there? And
Fluoride would be one of them.
fluoride.
Fluoride? Chloride?
Fluoride.
Chlorine.
Yeah.
Chlorine.
Head.
Might be Cl. All right. This is where I get crazy geeked out, but I don't teach that level, so sorry, Charlie. Because I'm not certified in that, and I like you guys. I like younger age kids more than you guys get like
Smart.
mean when you're over there.
Yeah.
You do. I don't know what happens to you, but you leave here and you guys get mean. I hope you don't, but you probably will. I'm kidding. I love you. You won't. You guys won't. Some of you won't.
Yeah,
It's just a whole different world over there. Anyway, okay. So that's matter. It makes up everything, and it's all made from this stuff here, the periodic table of elements. All of these are the different elements. And I can say, it's not just colored for a reason. You notice that the H is yellow over here. They're different like families that have different properties that are similar.
They have family too.
They have families too. Okay?
Oh.
But you will learn about this probably with the other Mrs. Fish over there or some other science teacher. I don't know. But this is fun, exciting stuff in my opinion that you guys can look forward to over there.
Yeah, we're talking silver figure.
Seven of us.
Now, moving on, conservation, which we already learned in our last chapter. Conservation means we're going to save something, right? Conservation of matter, saving matter. What could we possibly mean by that? Who wants to read? Zico, come read. Conservation of matter. We're at conservation of matter.
Chemical change?
Physical changes.
Physical changes. During a physical change, the amount of matter in an object stays the same. This happens because no new matter is being formed. When you cut a piece of paper in half, you still have the same amount of paper, just in two pieces. The fact that the amount of matter stays the same is called conservation of matter. Imagine you have a pile of building blocks. You build a tower using all of the blocks. Then you are asked to take apart the tower and build another shape using the same number of blocks. The new shape looks totally different than the tower, but still has the exact same number of blocks in it. This is a conservation of matter during physical change.
All right. So, thank you, Zico. Look at these pictures, and it says an orange is being weighed on a scale. And on the scale, I think it says it's 4.4 probably grams. And then they peel the orange, and they've got the orange and the peel both sitting on the scale. And it says, now how much does it weigh? Well, it still weighs the same because the peel and the orange itself are still sitting there. That's a physical change, right? We changed the orange. It's not exactly the same anymore, but it still weighs the same. Jason, chowing down on chips back there. If we were to put his bag of chips on the scale unopened and weigh it, it has the weight on the bag. It'll tell us how much it weighs.
That's not accurate.
Yeah, but there's air in it. And then when you open it, doesn't it get lighter?
Yeah.
And there's air in it that we can't weigh on a scale. You're right, because when we open it, that little bit of air escapes. So it might be slightly less.
Again?
Now, hang on. In theory, if I had a scale that measured fine enough, if I weighed myself right now, it would say a number.
What number?
That's not
A big one. And then I weigh myself right now, and it would be even bigger.
Is that compliment or a? Is that just
And then I weigh myself again, and I'd weigh even more.
So drink a gallon of water. Is that a serious
I'm
compliment?
getting not thirsty at all anymore. Because now, and my water bottle is getting lighter and lighter. I'm getting heavier and heavier because the water is now in me. Now, it really doesn't matter how much Miss Bad weighs. Okay, now, check this out though, guys. Check this out. There are other less easy to see physical changes. So look at the bottom of the glass or the paper. These are materials needed for an activity. It's sugar and water. What you can't see are their sugar cubes there, okay? It says the sugar and the water will be added together. What is their combined weight? So it looks like 14.15. And then they add the sugar into the water. What happens when you put sugar in the water?
Nothing.
Do the cubes sit in the water or do they dissolve? They dissolve. But it still weighs the same. You
Because they're
can't
tiny particles.
you can't see the big sugar cubes anymore,
They're particles.
but they have turned into tiny particles that we can't see anymore that dissolved in the water. So
And they
even though we
still
don't
in the
see the
sugar.
sugar,
They're still there.
it's still there. You got it,
Yeah,
Mace.
like you can taste
Water.
the sugar if you drink it.
Right, if you drink it, you can taste the difference.
Like salt water.
Like a salt water would weigh more than plain water because it would have salt in it. You can, and again, in salt water, you can't see in salt water, can we see the salt, Macy? No, we only know it's salt water if we taste it. Maybe smell it if the salt is strong enough, if there's enough salt in it. Okay. At the ocean, there's definitely like a saltwater smell that you can smell.
Salty water.
Okay, what about conservation in a phase change? We're gonna have to rewind to our third grade brains to remember phase change.
Oh, kind of like the phases of the moon. It changes.
Like the phases of the moon, it changes. But what are we talking about when we say phase change right now? Who wants to read? Kendilly, come on down.
The
All right,
convers-
hang on, wait, nobody's listening. Are we ready? Okay,
the conversation of matter
Jason.
also applies to phrases changes. Remember that changing from a solid to a liquid to a gas are all physical changes? The matter does not change, only the speed of its particles. If you were to melt solid gold to a liquid, you would see that it has the same weight as the solid.
All right, good job, Kendilly. All right, so phase changes are when it changes from a solid to a liquid to a gas, etc. So if I were to take a cup of water and weigh it, and then I put it in the freezer and got an ice cube, that ice cube would weigh the same as it did when it was a liquid. Okay? Now,
Can I read those next four
Hang on.
sections?
these next four little things.
Yeah.
I'm going to read those. You can read this next one. I'm going to read these because I'm going to talk about them as we go. So if you look at that, I'm sorry, there's more than one person talking.
So, block of gold would be pretty heavy, right? And then if you melt it in a cup, it would still be, like, would it feel that?
It would still feel exactly the same. So yeah, so if you melted gold, like if you're holding a piece of gold, it's like solid, it's pretty heavy. I'm assuming, I've honestly never just held a block of gold. But I think it's kind of heavy. And then if I melted it around, it would have the properties of a liquid. It would like slosh around in the cup that I melted it in or the pan I melted it in. It would have liquid properties. I could pour it, it would slosh around, but it would have the same weight. I would need the same amount of strength to hold it as I did the block. Okay. So if you look at that first picture, it's water, or no, it's ice in that little beaker cup. Okay, and it says that it weighs 215 grams. And then they just left it sitting there, so of course the ice melts because we're at room temperature. So now it's partially melted, partially solid in the second picture. So there's some liquid water. You can see if this was a color picture, you could see it better. And it's still 215. In the third picture, it's now showing that they've heated it up. It's near its boiling point, and it's still 215. But in the last picture, the weight changes. It says the water is at a full boil.
The air.
Its temperature has gone up. Why is it less than it was? Hang on.
And the steam.
Zeke, why is it less?
Because it's like evaporating into the air, and steam is the matter. Like the water changes to vapor.
Okay, so the water is changing from a liquid into a gas, which is steam. And as the steam, what does steam do? It rises and it's evaporating into the air.
Wait,
So some of that water, weight of the water, is going into the air as a gas and escaping the container. So it's not there anymore. If they boil that long enough, have you guys ever, or has your parents ever left a pot of water boiling on the stove for too long and it like boils down
Yeah.
and then there's nothing in the pot at all? Yeah.
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 Miss Bab, I have like a thing.
Okay.
So like, do gases like usually like, are they usually like denser than air? Because if you think of hot air balloon, like the vapor from the fire, it
Yes.
makes it float.
Yes.
And, like, would water vapor, like, if you made a balloon out of water vapor, would it float?
A balloon out of water vapor.
Well, if you filled up a balloon with water vapor, if you could, would it float like helium? And
That's a good question. I don't know. Heat rises. That's the whole reason hot air balloons work. But it should be lighter, and that's why it rises. Because the denser things are going to stay down because of gravity.
yeah, it's lighter. That's why.
Yeah.
Heat rises, and helium it's lighter than the air.
Yes, helium is lighter than air. Okay, DJ, I gave you dibs on reading next. Come on down. Conservation of matter, chemical change.
Chemical changes also demonstrate the conservation of matter. Remember that in a chemical change, new things are formed. However, if you were able to collect this new matter and weigh it, you would see that it has the same weight as the original materials. One needs to be careful here, though. Many times during chemical changes, some of the matter is lost as gas. Therefore, the final weight of the new matter may appear to be less than the original. For example, the weight of ashes collected after burning paper will be less than the original because some of the weight is lost in gas.
Okay, perfect. Thanks, DJ. So kind of what we just showed. So when water boils, some of the weight is lost. It doesn't disappear. It just went into the air as a steam, right? So matter wasn't destroyed when we boiled the water. It just turned into steam and went into the air.
Yeah,
So
when
matter
the paper
creates
burns,
new
the
matter whenever
smoke,
it's changed.
and when
Right.
the paper burns, the smoke goes up.
Right, and when paper burns, the smoke goes up. So where it's talking about, think about in third grade. In third grade, I remember when we talked about chemical changes and something new being made, we used, at least in my class, we used the example of baking. I can put together sugar and flour and baking powder and baking soda, and we can make, what did we make in third grade? Do you remember we made pancakes that day?
That's
what we did.
We made pancakes. I know Miss Holt's class made pancakes. I think we all did. I think all of fifth grade did.
Fifth grade.
To show that in third grade, when we were in third grade, I'm positive Miss Holt's class did it because me and Miss Holt did everything the same. Anywho, he made pancakes, and that was a chemical change because once we put those things together, once a pancake is made, can I separate it back out into flour and sugar and milk and baking powder? Nope. It's something brand new. I had mixed things together, created something brand new. It was a chemical change. Now, what they're saying here is, if I were to take the flour that I'm going to put in the pancakes, all the sugar, all the milk, and I put all of that on a scale and weighed it, all of the individual ingredients, and I weighed them all, and then I took all of the completed pancakes and I weighed all of them, it would be the same. The ingredients should weigh the same as the actual pancakes.
were fluffier.
But the pancakes are fluffier, so what? It's still all the same stuff, they just combined it in a different way. Now, what this is saying is you might lose a little bit of weight because as you're cooking, isn't there a little bit of steam?
Like if you're mixing flour in a bowl, some of it like.
And right, and as you're mixing and stirring, when you pour the batter out, isn't there always like a little bit that's still like stuck to the sides of the bowl? Like you never get every single drop of batter onto your skillet or whatever.
Sometimes when you're mixing flour, even if it doesn't go out the sides, it makes dust.
Right, yeah, and sometimes the flour kind of poofs when you pour it in a bowl or mix it. So you might lose a little bit of it, but if you could, it should weigh exactly the same because matter does not disappear. It is not destroyed. It might change shape. It might change form from a liquid to a solid to a gas. It might even turn into something entirely new like a pancake, but it's still there. whatever element makes up flour is still there. It's just part of the pancake instead of part of flour molecules.
Isn't it made out of like?
I'm making you hungry. It will be lunch in like an hour. Okay, so let's look at, yeah, Grace,
What
Grace,
is trees made out of?
what is what?
Trees made out of?
Air, wood.
I don't know what elements make up each individual thing. That I don't know. You'll have to
So,
look up what
you're
elements
blocking
make up.
Hermes. You're blocking Hermes.
No, Hermes is on the table.
Oh, yes?
Yeah, no, he's done it. Okay, let's look at these pictures under chemical change, okay? The total weight of a balloon full of baking soda and a flask of vinegar is shown. Notice the weight on the scale, 178. So what they've done is they've filled the flask, the glass thing, with vinegar. And then they poured baking soda into the balloon. I don't know how easily you can see it, but they've got the balloon attached to the top of the flask, and the baking soda is in the top part of the balloon that's flopped over, okay? Now, what they do is they dump the balloon upside down so that the baking soda falls into the vinegar below it. And when it does, they produce a liquid and a gas. There is a chemical reaction between baking soda and vinegar. You may or may not have already known that. So when this reaction occurs, instead of the gas going into the air, where is the gas going?
Into the balloon.
Into the balloon. So the balloon is actually being blown up by the gas that's trying to escape
And then
from the chemical reaction.
And then it will pop in the gas will.
Now, okay, so it shows right now that it still weighs 178 with the balloon blown up because the gas is trapped there. If, like Zeke says, we were to pop the balloon, would the weight stay the same?
No.
No, why not?
Slow down and like all the air will go.
The gas would float out and we would lose the weight of the gas into the air. You are correct. What if we dumped the baking soda and vinegar in an open container with no balloon? Would the weight stay the same?
No.
No, why not?
Because the air,
The air will just leave.
Right, the gas part of it will just go into the air and we won't be able to trap it. Okay. All right. That is what I have for today. We're discussing that. The last question that's on here is, so how does the conservation of matter relate to phase changes? So rewinding back to the very first change we talked about, phase change was solid to liquid to gas. If I have an ice cube and I let it melt, is any matter being destroyed? Water. But I have water. I don't have ice anymore, I have water. I didn't destroy the ice and create water.
You melted it.
Melted it, it's still the same, right? It's still the exact same molecules.
Thing, but in different forms.
It's the same thing, but it's got different properties now, okay? Now I'm gonna heat it up, and it's turning into steam,
Which is a gas.
which is a type of gas, so it's changing phases
What types
again.
of gas are there?
But how many types of any of those elements can be turned into a gas form, a solid form, or a liquid form? They each have their own melting and boiling points. Every element has a
What is
melting
the
and boiling
boiling
point.
point of oxygen?
titanium?
I don't know.
Like iron, it has liquid iron.
Yeah.
It doesn't technically have iron.
again, iron can.
There are certain ones that they will make you memorize boiling points and freezing points of when you get to
Some
that
of them
stage
it's
in
like
your science
a
life.
Some of them
Science.
That I don't remember anymore. You want boiling and freezing points, I can give you water. That's it, because that's what
What
you
water point?
water boils at 100 Celsius and freezes at 0 Celsius, or 32 and 212
It's 200.
if you're going Fahrenheit scale.
I thought it was 200. Oh, 17.
I think it's 212. Yep. I could be wrong. Okay, battle. Showdown between Bab and Bop.
Bab and Bop.
Boiling point of water.
Yeah, I messed up.
Bab wins.
Wait, Bab, can you search the boiling point of iron?
Can I search the boiling point of iron? I can in a minute. Okay. So does everybody understand the concept that matter is neither created nor destroyed. It's always there. It's just changing. So let's rewind, because yesterday some of the boys thought they were being super cute. And they were like, but babies are created. So where does the material, okay, Sean. So now, because you were cute yesterday, now I've got a big question for you today.
Oh.
And we're going to see if you can answer it. And we're going to see if you can answer it just as cutely as you posed the question yesterday. Let's do this. You come on down. Come on down.
Oh. Walk on down. Unnecessary items.
All right. Okay. My question for you is this. If matter is not created nor destroyed, if that is true, which we know it is, okay, where do babies come from? Mommy's tummy isn't the answer. The matter that makes up a baby. Okay, and I don't need you to say explicit, not fifth grade words. I want to know. Listen carefully. Look at me.
Go to page 90.
This is serious, yo.
No, I want to be
No,
a
come here. We got this. The matter. I know you do, Cam. We're gonna make Sean suffer a little bit. Though. Hang on. The matter that makes up a human baby, where does that come from?
I don't know. The periodic table.
No. Periodic table is not the answer.
Daddy and mommy.
I don't put a periodic table in my belly and say, "Come on, baby." Okay. Where did that matter come from? Think of it. What are our bodies made of?
Carbon.
So what is a
Babies
baby?
are made out of carbon.
And so babies are also made out of carbon. So are they using some of the materials that are already within the mama? Oh, they are? And then as mama keeps eating for 9 months, then the baby keeps growing because mama's bringing in more matter to feed the baby. I don't need the real science behind it, guys. Calm down. Like, we're not going, like, this isn't that kind of class. You guys, you thought you were going to be funny yesterday, and I'm just telling you. So where do babies come from? Carbon, oxygen, nitrogen. All my elements on the periodic table. Okay? But that matter, when a baby starts, right, it's a tiny thing, whether it's a kitten baby, a human baby, a puppy.
A human baby is as small as a grape.
It starts so tiny, it's the size of one of these particles that we were talking about, right? And it grows from there. So, it's pulling the matter that it needs from within.
Does the mom get smaller as she's having a baby?
No, she doesn't, because she's consuming way more calories throughout the day. Mamas usually are supposed to gain, really they're not supposed to gain other than the actual weight of the baby that's inside of them. Okay. And then obviously when the baby is born, then they lose that weight.
No, because the tummy's so big after that.
Well, the tummy's stretched out. They've got it, but it's empty. It's just extra skin. So they weigh a little bit more because they have more skin, because their skin had to stretch to fit the baby. Okay. So yes, so they are going to weigh more because they put more things into their body, and not every piece of what they put into their body does the baby end up using.
Or the baby's mouth just goes like.
And nope, not it. All right. Does everybody understand what we're talking about here? Matter is not created nor destroyed. It's always been here. It just might have changed a little bit along the way. That's what I've got to say about that. I'm going to hit stop record before they get me into trouble with this baby conversation. All right. Goodness gracious, you guys.